So, how does your AI remember information? In this video, the objective is to help business owners understand embeddings and memory in AI. The key outcome that you'll get in this video is you'll have an understanding of how AI stores and retrieves information, starting with the memory problem. Now, have you ever met someone once and remembered them perfectly? You know, you remember what they looked like, what they talked about, how they made you feel, the interesting details. Your brain doesn't store photos, it stores essence, a memory of who they are. Your AI has the same challenge. So, how do you make it remember information in a way that helps future decisions? Not as raw data, but as memory. And this takes us to, and so we're going to start with embeddings. So, what are embeddings? Embeddings are is essentially a mathematical way to represent complex information such as words, customers, products as numbers that capture meaning and relationships. Your AI remembers using something called embeddings. Think of it like a personality profile. Person A likes adventure. Maybe if you had to rate it out of 10, person A likes adventure 8 out of 10, prefers luxury 4 out of 10, values sustainability 7 out of 10, wants speed 9 out of 10, cares about style 6 out of 10. Then there's person B, which is customer 2. Um, they might like adventure 30% of the time, prefers luxury 80% of the time. This would be 8 out of 10. Value sustainability 20% of the time, 2 out of 10. One speed 4 out of 10, which is 40% of the time. Cares about style 90% of the time, which is 9 out of 10. Now you can compare them, person A and C, similar on adventure or speed. Person B and D, similar on luxury or style. This is an embedding, a representation of someone as numbers that capture their essence. Your AI does the same thing. For customers, it creates a 50-dimensional profile. Each dimension is some trait or preference. Together, it makes a unique profile. It can compare customers to find similar ones. For products, creates a profile. Each dimension is a product trait. Together is the essentially the essence of the product, and it can be compared to other products to find similar ones. And for search queries, there's red running shoes become the embedding, can find products matching that intent, even if exact words don't match. And so, what's the magic of embeddings? Similar customers get similar embeddings, similar products get similar embeddings. Recommendation, essentially finding customers and products with similar embeddings. For example, your product embeddings could be like your Nike shoes, sneaker 9, luxury 3, durable 8, style 7, speed 8, Prada heels 2, luxury 9, durable, you know, also the running watch, these are the same categories, you know. And so this leads us to how are embeddings created, you know. So embeddings are created firstly starting with raw data. Customer A bought XYZ. Customer A has the age, income, location. Secondly, that you train the model to predict behavior. Given what we know about customer, will they buy Z? Model learns to represent customer as numbers that predict buying. Thirdly is you extract the representation. Take the memory the model created, that's the embedding. It captures meaningful patterns. And then fourthly, you use for recommendations. Find customers with similar embeddings, find products with similar embeddings, then match them. So why is this powerful? You know, um, the old way is customers like shoes 0 to 1. You'd recommend shoes. The new way is the customer is represented as 50 numbers capturing taste, preferences, find products with similar embeddings, and the recommendations become more personalized. Better matches equals more relevance, which equals higher conversions. And so essentially the new approach with embeddings is the customer is represented as 50 numbers capturing taste. You find products with similar embeddings, personalized recommendations, much better matching, higher conversions. And it's all illustrated here. It captured a semantic meaning, foundation of modern AI, NLP, recommendation search. And yeah, this takes us to vector databases and memory system. And so, what is a vector database? A vector database is a specialized database optimized for storing and searching embeddings, enabling fast similarity matching at scale. And so, once you have embeddings, you need to store them and search them. This is like organizing a library. You know, the old library may have no organization, books stacked randomly. To find a book on gardening, you have to search every stack. It takes hours. And then there's the new library where books are organized by topic. Gardening books are together, philosophy books are together, science books together. To find the gardening book, you go to the gardening section, and it takes minutes. Vector databases do the same for embeddings. They organize embeddings so similar ones are near each other. When you search for customers like this one, the database returns similar customers instantly. And so this is all about the vector database magic. Now, without the vector database, you search through all embeddings sequentially. 1 million embeddings equals 1 million comparisons and takes seconds or minutes. With a vector database, you use special indexing and algorithms. It organizes embeddings for fast similarity search. 1 million embeddings are searched in milliseconds. And so traditional databases, they store customer ID, the name and age, the query. You get customer one, the speed, instance with a direct lookup. Then there's the vector database where the store has the customer embedding. The query find customers like the embeddings, return with similar embeddings, returns 10 most similar customers, and the speed is you get this information in milliseconds. And so real systems using vector databases are, for example, Netflix, they store movie embeddings. They store movie embeddings capturing genre, tone, pacing, etc. The store They also store user embeddings, which is capturing taste. The query, they find movies like user X likes, returns perfect recommendations. With Spotify, they store embeddings such as genre, mood, artist, tempo. They store the listener embeddings, which is like their taste profile. They query what songs should user Y hear, returns a perfect playlist. Amazon, they store product embeddings such as category, features, reviews. They store customer embeddings, preferences, the history, what products um customer Z likes, and they return perfect recommendations. And so the business impact is better recommendations equals higher engagements, which equals more revenue. Netflix, a 1% improvement in recommendation relevance equals over $100 million in revenue impact because users watch more and cancel less. Spotify, better playlists equals more hours listened equals more higher engagements, which equals more ad revenue. Better product matches equal for Amazon equals higher click, higher conversions, and more strategic advantage. And then there's a technical advantage where organizations with good embeddings and vector search have better personalizations, higher conversions, lower churn, and more for competitive advantage. And so this leads us to keeping memory updated. So, which leads us to the embedding shift. So, what is the embedding shift? Embedding shift, the embedding drift is the changes in customer preferences, product characteristics, or market conditions over time, requiring embeddings to be updated regularly. And so here's the problem with embeddings, right? Which I'll go on with using an example. They're based on historical data, but people change, products change, markets change, and a customer's taste in 2024 might be different from 2023. A product's market position changes over time. If embeddings don't update, AI recommendations get stale. For example, a fashion retailer, maybe in January 2024, the customer embedding shows that indicates that the customer likes winter fashion. The recommendations would be heavy coats, warm sweaters, and it works great. June 2024, customer embeddings still indicate that they still thinks the customer likes winter fashion. The recommendations still heavy coats, warm sweaters, but the customer wants summer dresses. Hence the recommendations fail. And so the solution is essentially to refresh embeddings regularly. How often? Real time, every transaction, which is um expensive and it's more suitable for larger enterprises like Netflix or Spotify. Weekly, every Monday is a good balance. Monthly, standard practice, which is standard practice. Quarterly, every 3 months is a bit lazy but cheap. And so there's a real cost comparison here. Real time embeddings could cost anywhere, it could cost 50K per month with the accuracy of 95%. Use cases being Netflix and Spotify because of their high volume. Weekly embeddings 10K per month, accuracy could be 90%. Use cases at most e-commerce, right? Monthly embeddings could cost 3K per month, accuracy 85%. Use case budget conscious. The quarterly embeddings could be $0, which is like essentially a batch process. Accuracy 75%. Use case very cost conscious. And so the key insight here is you don't need real time embeddings for most use cases. Weekly or monthly updates capture 90% of the benefits at 5 to 10 times lower the cost. And so your AI remembers, just not every second, and that's fine. Because your customers' preferences don't change every second either, they change over weeks and months. And so you match your update frequency to your business reality. And so and so by now, what you should understand is AI remembers using embeddings, which are mathematical representations capturing meaning. Embeddings enable similarity, matching, and recommendations. Vector databases store embeddings for fast search. Embeddings must be refreshed as the world changes, and the update frequency is for real time is usually used by larger corporations such as Netflix, Spotify for scale. The weekly, most e-commerce, monthly standard practice, quarterly budget conscious.